everyone, in this video we're going to talk about polynomial functions. So first we want a definition of what the equation for a polynomial function looks like, and that's what we'll work on right here. And then we want to work on looking at the equation and being able to have a pretty good general idea of what the graph looks like. So both the equation and graphs of polynomial functions, what we want to pin down in this video. Okay, so this first one, we get this complicated looking equation, and this is supposed to give us an idea of whether or not something we're looking at is a polynomial function. And even more specifically, it's supposed to tell us that it's a polynomial function of degree n. So degree is a really important distinction between polynomials. You can have second degree polynomials, those are your quadratics. You can have third degree polynomials, those are your cubics, and so on. So you can have all these different degrees, and that will determine some specific things about the graph. So when I'm looking at this thing, really what I want you to get from it, first of all, is that this degree n has to do with the biggest power you see attached to your variable. So the biggest power you'll see is an n. You could then have an n minus 1 and an n minus 2 and so on, down to a first power, and then here you could imagine there was a 0 power. This is your constant term, so no variable x in here, just a constant. So it doesn't matter what order you write the terms in. It doesn't matter if it's the first one or if it's the last one or if it's somewhere in the middle. Wherever you see the biggest power on your variable, that's a really key term that's going to tell you some good information about the graph. And it's also telling you specifically what the degree of your polynomial is. With the a sub and the subscripts, the a's with the subscripts here, this is basically trying to build up the same idea as when we say the standard form for a quadratic is ax squared plus bx plus c. The reason we don't just stick with this ax squared plus bx plus c or ax cubed plus bx squared plus cx plus d type of using the letters of the alphabet to represent our coefficients is because that limits the number of terms we can have. And really, a polynomial should be able to have as many terms as we want. So it could have an x to the 100, which means this would drop all the way down. We'd have 100 different coefficients and then our constant term. So that's what we're doing here. We're saying, okay, well, we'll just call them all a's, but we'll use a subscript to show that they can all have different values. So we'll have, if it's cubic, an a sub 3, an a sub 2, an a sub 1, and an a sub 0. And again, they all get the letter a to give the idea that they're all part of this same group of constants. Sorry, this is what I was actually going for. They're all real numbers. They're all constants that we would know. And then the subscript is showing that each one can be a different constant. In fact, a bunch of them could be 0. You don't have to have a term for every single power, but it is really important that this very first coefficient is not 0, because if it were, we wouldn't actually see the x to the n, and it wouldn't be nth degree anymore. So that's the only one that's not allowed to be 0. If it's nth degree, it has to have an a sub n. Could be 1, can't be 0. Okay, so this is what polynomials look like. N has to be a positive integer, and we stop when we get down to this first, and then you can even think about it again as the 0 power here. So we're never going to see any negative powers. They're all going to be integer powers. If this one is 5, then this one will be 4 and 3 and 2 and 1. And again, if any of the coefficients are 0, you might skip powers, and that's okay. But we do need to have powers be positive integers. Okay, so there is a bit more on this first page. There's kind of a summary of things that you should know about the graphs of polynomials by the time we get all done. So I'll jump back and forth to that. I do want to remind you really quickly before I move on to some examples that we already know the shapes of some really basic polynomials. We know the power functions. So we know what y equals x squared looks like. And we know what y equals x cubed looks like. And if you'll remember, we also talked about what happens if we go up to a 4th power. The answer is it flattens out a little on the bottom and then gets steeper on the edges. I don't know if that's going to be very clear here. And an x to the 5th looks a lot like this. It's a little flatter in the middle and then a little steeper on the edges. My x cubed actually looks a little funny. It should flatten out a little bit more in there maybe. So in general, if you have an even power, you're going to get one of these y equals x squared or x to the fourth type shapes. And if you have an odd power, you're going to get one of these y equals x cubed or x to the fifth type shapes. And these are going to help us with some of the stuff we're trying to figure out about graphs. So keep those in mind, and we'll come back to some of this list after we've looked at a few graphs. Okay, so to get us started, this is a little different approach than the transformations thing. So we're not going to take just a basic x cubed graph and transform it. We want to talk about, well, what happens if you have an x cubed and an x squared and an x and a constant all in the same equation? That's not just a transformation of an x cubed or an x squared, that's some combination of those. So to get us going on what the shapes of polynomials should look like, I'm just going to use my calculator to graph a few of these things. And as I do that, I'm going to look at what's the degree of the polynomial and then figure out how many zeros, remember zeros are x-intercepts, and local maximums and minimums there are. And then we're going to zoom out until we can see the global behavior of the graph. Okay, so we can actually answer part A right off the bat here. Remember, it doesn't matter what order your terms are in. You're looking for the biggest power on your variable. So this right here is telling me that the degree is 3. Okay, so that's A. For B, let's check out the graph. Let's see. So if I want a 3 plus x minus 4x squared plus x cubed, okay, so we should be able to type it in exactly like that. And then for now, I'm just going to hit zoom and do a zoom standard. Zoom standard will show me everything from negative to 10 on the x-axis and negative 10 to 10 on the y-axis. So this is pretty good local behavior. I think I'm seeing all of it. By the time we get done with some of the properties of polynomials, you should have an idea of when you've really seen it versus when there might be another little local maximum or minimum off somewhere else. So looking at this, you'll just have to take my word for it now. I can count off zeros. I see 1, 2, 3 x-intercepts, so 3 zeros. And local maximums and minimums. I see a local max and a local min, so 2 max, mins. Okay, and then I'm going to draw just kind of a rough sketch of this one so that we can look back at it if we want to. Okay, what was it doing? It was going like this. Okay, again, just really rough sketch. Okay, and then we're supposed to try and zoom out until we can see global behavior. And basically the idea here is to zoom out far enough that you can't even see the little maximum, the minimum, the x-intercepts. All you're seeing is the really big picture shape of this thing. So you can just zoom out, but the problem with that is you can see already we don't need to see nearly this many x values to fit our y's from negative 10 to 10. So actually without adjusting my x at all, if I just start increasing my y min and my y max, I'm going to get a little better idea of what's going on. So I'm going to hit window and I'm going to leave x's alone for now. And I'm going to make the y's go, let's go negative 100 to 100. And this is just kind of a trial and error process. Already getting pretty good. It's hard to see that maximum and minimum in the 3 zeros. I'm going to go a little more. Let's just tack on a 0. And really, even without being this far zoomed out, you can get an idea of what the global behavior is. I just want to make sure I zoom out to the point where you're not distracted by the zeros and the local maximums and minimums. Looks like I do want to adjust my x's just a little bit. Oops, negative 20 to 20. I might regret this, but I want to zoom out a little bit more even on the y. Oh, negative 5,000 to 5,000. Okay, that's pretty good. So notice what I'm seeing now pretty much looks like an x cubed shape. I'm not seeing the extra bends and the zeros. All I'm seeing is that the basic shape of this thing looks an awful lot like a y equals x cubed. And I really want to emphasize that when I'm talking about global behavior, I don't care that much about what's going on in the middle. I don't care about any of that local stuff. Really, the big thing this is telling me is that as x gets really, really big, as x gets gets really, really big, so it goes to positive infinity, we're headed out this way on the graph. Our y also gets really, really big. This is the beginnings of some calculus notation. This x goes to infinity, y goes to infinity. And as x gets really, really small, y gets really, really small. Let's see if I can write today. This again is just saying as we head to the left on our graph, our y values head down to negative infinity. Okay, so there's the first one. So again, that was a pretty good looking polynomial shape, nice curve, couple of bends. Let's look at the second one. Okay, so this one actually is a little tricky on just spotting the degree because it's in a factored form. So you have to imagine multiplying all of this out if you're going to be able to see what the degree would be. So you don't actually have to do it, but being able to imagine how that would work is really important. So you could multiply in whatever order you want. Excuse me, doing these at night again always makes me yawn. So here's a pair and here's a pair. This is not your only choice, but I'm thinking I would imagine saying I have an x and then an x squared plus x minus 2 and then an x squared minus x minus 12. And then you could distribute your x in. So you'd have an x cubed plus x squared minus 2x. And then you'd have to multiply this entire trinomial, 3 terms, by this entire trinomial, which basically means you mentally block this together and you distribute it in. So you'd multiply the whole thing by an x squared, the whole thing by a negative x, and the whole thing by a negative 12. I'm not going to show you all those steps, but I am going to say that we're looking for the highest power. So the highest power we're going to get from that is when we actually multiply the x squared, the x cubed and the x squared together. So it's a 5th power. And you can, once you catch on to how this is all going to work out, just count this out. I'm going to multiply an x by everything in each one of these parentheses. So an x by an x, and an x, and an x, and an x. 5 x's are going to get multiplied together. So again here, the degree is a little hidden, but we can absolutely spot it. The degree is 5. Okay, so if we want to type this one in and graph it, again, you don't have to do anything. You can just type it in as it appears. So x times x minus 1 times x plus 2. Oh, sorry, guys. Times x plus 3 times x minus 4. Okay, and I'm going to go back to my Zoom standard to get started. Again, you're not always going to see all of the key information on a Zoom standard, but it's an okay starting place. And if we start to get more comfortable with going from equation to graph of these things, we'll have a better idea of whether that's going to show us everything or not. So right now, it looks like I'm seeing 1, 2, 3, 4, 5 zeros. And I could guess right now, I'm going to try and fix the graph so I can see them, but it looks like I should have one maximum and then a minimum and another maximum and another minimum. So I'm guessing 4. But let's go ahead and play around with our window. I'm fine with my x's again. I need to adjust, in fact, I need to adjust both of these, y min and y max. Okay, so that was decent. I caught the top, bottom, top, and then there's one down here that I'm still not catching. So let's see if I can do that. Let's go negative 50. Still looking like it's a long ways off. Here's negative 100 as my y min. Still looking like it's a ways off. Negative 200. Okay, so there we're catching all of the local behavior. And again, for now, you're just going to have to take my word for it that that's all of it, that it doesn't turn around somewhere else. I'll give you some guidelines to help you decide when that's true or not in just a minute. So I do see 1, 2, 3, 4. 4 max mins. Okay, so that's my local behavior. I have 5 zeros, I have 4 maximums and minimums. I now want to zoom out even more until I get to the point where I can't really see all the different maximums and minimums anymore. That's all been mushed together, and I just see the general shape of the global behavior. So I'm sure I'm going to want to go a lot further than that, but let's start with negative 500 to 500. Okay, and it's starting to mush in, but I can still see it wiggling, and I can definitely still see that one. So let's go negative 5,000 to 5,000. Not bad. I can still see it a little bit. I'm getting a pretty good idea here. So if you want, you can absolutely keep going. Negative 10,000 to 10,000. There's a tiny bit there, but I'm feeling pretty good about saying that this shape looks an awful lot like the last one. So something like an x cubed. So this one, we definitely had this kind of shape going on. And here I'm seeing the same thing, but I actually wouldn't claim that that's an x cubed shape. I would say I have this 5th degree polynomial. Maybe what I'm seeing is that x to the 5th shape. Okay, so that tells me kind of the same thing as last time. Really, the big thing about global behavior is it just tells you where to tack these arrows on the end of your graph. So you should have an arrow saying that as x gets big, y also gets big. And as x gets big negative, y also gets big negative. Okay, so we've got a couple to look at here. Let's see if we can summarize. What we're really looking for here is a relationship between the degree and the local behavior and the global behavior. So based on the two examples we've got, notice when our degree is 3, it looks like an x cubed. We get 3 zeros and 2 maximum minimums. When the degree is 5, it looks like in x to the 5th, we get 5 zeros and 4 maximums minimums. So based on just looking at this, I would say it looks like the degree is going to determine the number of zeros, and then you'll have one less max min, and the degree also determines your global behavior. Unfortunately, the rule isn't quite that straightforward, so I want to show you one more example, and then I'll give it to you. So last one here, this is, let's see, highest power. This is 4th degree. So this is my leading term. This negative 1/4 is going to be important. That's called your leading coefficient, the one that's hooked to the biggest power. Okay, so I have a 1/2 x squared minus x cubed minus 1/4 x to the 4th plus 4. Sorry, you couldn't see that. Okay, so there it is. And I'm going to start off again with my zoom standard. Oh, interesting one. Okay, so it looks like I'm missing a maximum. Okay, so let's see. I didn't write this down. So this is 4th degree, degree 4, and the number of zeros. Okay, so it looks like I have 2 zeros, and again, for now, you'll just have to take my word on it that I'm not missing anything. I planned these so that I'd see all the local behavior without too much work. And it looks to me like I'm missing a maximum up at the top. So let's see if we can just raise our y max. Yeah, that was pretty good. Okay, so I'm seeing a local maximum, and then this one messes with people a little bit. That's not a local max or a local min. If you draw a circle around that flat spot, it doesn't matter how small you make the circle, there will always be points on the right side that are smaller than the y value of that, have a y value smaller than the y value of the flat spot, and there will always be points on the left that have a y value bigger than that y value. So that is a flat spot. It is interesting. It's an inflection point. You switch from concave up to concave down, but it's not a local max or min. So I'm actually only seeing one. In this case, it was a local max. Okay, so you can see that this one doesn't follow the rule. Let's go ahead and do our zooming out and get our global behavior, and then we'll go let's do big. Let's do negative 500. We'll go for the generalization. Okay, so pretty good. I'm starting to lose that one. Let me just go a little bit further. Here, we'll just go negative 5,000. Oops. Good plan, except now I need to expand my x's out a little to see what's really going on. Okay, so what I'm seeing here looks like my even power shape, my x squared, x to the 4th, x to the 6th type shape, but it's upside down. So this is looking like, and again, it's not a coincidence that we're seeing the degree match up with the global behavior here. What we're seeing looks like an upside down x to the 4th, which means in this case, as x gets really, really big, y goes to negative infinity. And as x gets really, really small, y also goes to negative infinity. So I didn't sketch the middle one here, but this one is doing something like this. Okay, and this one was crossing at negative 3 and negative 2 and 0 and 1 and 4. So just like with quadratics, if you have this in factored form, you can just read off the x-intercepts. If you set this equal to 0, you would just take all 5 of these factors and set them equal to 0. And what was this one doing? It was going like this. So it came across, across. Again, this is really rough sketch. I don't remember exactly what it was doing. Something like that. Okay, so there's several shapes to look at. And based on this, we can start to get some ideas. And I'll give you the list so that you know for sure. Okay, so one thing is that the graphs should always be smooth and continuous. So that's the first one on our properties list. I'll show you the list in just a minute, but I just want to say the smooth and continuous part. Continuous means an easy way to think of it is you don't have to pick up your pencil to draw this thing. There are no asymptotes or holes or jumps or breaks in the graph. It's just one continuous piece. And smooth means there should never be a sharp corner. So even if your calculator, even if it's really steep and your calculator makes it look like a sharp corner, they're always rounded off. So smooth and continuous. Let me put this list over here for you. Okay, so that was the first one. They're always smooth and continuous. The domain is always all real numbers. So if we look at these, again, all we're doing is raising numbers to powers, possibly multiplying by some constants, possibly adding on some constants, and then adding all of them together. So there's not anything in there that you wouldn't be able to apply to any real number. There's no division, so we don't have to worry about dividing by 0. There's no square roots, so we don't have to worry about roots of negative numbers, no roots at all. There's no logs, so we don't have to worry about logs of 0 or negative numbers. So domain is always all real numbers. Let's see where we are. Okay, so we were working on this, at least I was. If your polynomial's 3rd degree, we had 3 zeros, 5th degree, we had 5 zeros, but the last one didn't follow the pattern. We had a 4th degree and we only got 2 zeros. So what can happen is you get an at most rule. So if it's 3rd degree, you'll have at most 3 zeros and at most 5 zeros, but you can have some of the squiggly behavior happen in a way that you don't cross the axis the full number of times. So you will always, for an nth degree polynomial, have at most n zeros. And then the other part of this is how many bends you'll get. Again, here we had a 3rd degree, we got 2 bends, 2 max mins. Here we had a 5th degree, we got 1, 2, 3, 4 max mins. So it's looking like 1 less than the degree, but this one again breaks the rule. We actually got 1 local maximum for a 4th degree polynomial, and what's happening here is it's almost like 2 of the bends got squashed together to the point where you just got a flat spot. So we could have here at most 3 turning points, but we only got 1. So both of these are at most rules. angles. If it's 4th degree, you'll have at most 4 zeros and 3 turning points. If it's 10th degree, you'll have at most 10 zeros and 9 turning points. So this is your rule to help you a little bit with, do I just need to zoom out to see more local behavior, or have I actually captured all the possible local behavior? This one, if x minus r is a factor, then r0 is a 0, might look kind of confusing, but it's just saying what I mentioned here, that if you have a polynomial in factored form, it's just like quadratics. You should just be able to straight up read off what makes each factor 0, and those are going to be your x-intercepts. Global behavior. So we caught on to the fact that the degree always matches with the global behavior, and then we had something funny happen in this last one. We did get x to the 4th looking shape, but it was upside down. So it actually ends up being determined by not only the highest power, but also the leading coefficient. So if you snag out this term, so this one right here, it's a negative x to the 4th. You can include the 1/4 if you'd like here. That's fine. I don't care either way. It doesn't change the picture in my head that much for this general shape sketch. I do need to know it's upside down x to the 4th. Here, we have to imagine it again. If we multiply this all out, it's x times x times x times x times x. None of them have coefficients, so it's going to be a positive 1x to the 5th, which is giving me this right side up x to the 5th. And then here it was a positive 1x cubed, which is giving me this right side up x cubed. So it's the leading term, the highest power, and the coefficient that goes with that power. There's one more on this list that I'll come back to when we get to it. Multiplicity is really helpful when we're graphing. So if we can get our polynomial in factored form, that's going to be our #1 tool for helping us graph these things. And once we get it in factored form, sometimes we'll have powers on those factors, and that will change the shape of the graph at the x-intercept. So instead of just crossing through, it could do something like this where it bounces. It could, well, in fact, this isn't even a cross through. So cross through would actually be more like a y equals x. So cross through, bounce off, or make these little x to the cube, x to the 5th type flat spots. Okay, so that was your intro video. We'll do more on how you actually would get this graph from scratch by hand without using your calculator in other videos. Thanks for watching.